Okay, thank you for joining us today. Let's go ahead and get started. Before we dive in, I do want to point out one last time that you have the ability to ask questions at any time during the program. I will answer those at the end. Today, joining me, we have Marcy. How are you doing today, Marcy?
I'm good, Chuck. How are you?
I'm doing great. Hopefully she can keep me on track. She's done a great job so far.
I'll do my best.
Let's go ahead and get started. Okay, let's take a look at our agenda today. Today's topic is all about Modbus, and we'll probably focus a little bit more on Modbus TCP, which is Modbus over Ethernet. But because of the way Modbus has been created and is formatted, really the things we'll talk about today will apply to both regular Modbus as well as Modbus TCP. So after talking about and describing the protocol and how it's used, we'll go into more specifics about setting up Modbus in the Horner OCS product. Now, I know a lot of you may be new to the Horner products. OCS is an acronym that we use for our main product. It stands for Operator Control Station, and the Horner Operator Control Stations is our product name for our line of all-in-one controllers. And those products combine the functionality of a PLC with operator interface, with all kinds of built-in I/O, remote I/O, and networking capability. And networking is what we're going to focus on today, at least one aspect of networking, and that's Modbus TCP. So once again, we'll talk about Modbus in general, and then specifically as it relates both in server and client mode with our products, the Horner OCS all-in-one controllers. We'll definitely go through some configuration and programming, and then have time for questions and answers. All right, let's get started. What is Modbus? Background and protocol details. Okay, Modbus was invented in the late 70s by Modicon. Of course, Modicon is now part of Group Schneider today, or Schneider Electric. I don't even know if they call themselves Group Schneider or not anymore. I know the first thing that I'd be thinking if I was attending this webinar, and that is, why in the world are we talking about a 40-year-old protocol? Well, effectively, even today, Modbus is the most common and the most popular industrial protocol for device-to-device communications. There certainly are better protocols, and absolutely, I would hope, there are more modern protocols for sure. But if you're a control engineer, even in 2020, you need to have an understanding of Modbus, because at some point in your career, probably pretty frequently, you're going to have a need to integrate products from multiple manufacturers, get them to share data, and the most common way that that occurs, today at least, is using Modbus. It's a protocol that can be used with a variety of different physical media. It can be used over radio. It can be used over the old-fashioned serial ports of RS-485 and RS-232. Of course, they're still everywhere today, especially 485. They can certainly be used over Ethernet with a couple of different transport protocols. Why is Modbus popular? Well, it's popular in part due to its longevity. It's been around forever. Its versatility, and its simplicity. It's easy to understand, and it's easy for manufacturers who, frankly, aren't communication experts, but are experts at creating some sort of industrial product. It's easy for them to understand in order to make data from their piece of equipment available to other pieces of equipment in the same system. So a lot of reasons, there are a lot of reasons why Modbus has been and remains popular. It is the common denominator of industrial networking. Okay, now let's dive into a little more of the details. Again, Modbus is very easy to understand. It's organized around 4 different types of memory areas, which is really patterned after traditional PLCs. You've got coils, patterned after digital outputs, inputs, patterned after digital inputs, input registers, which are analogous to analog inputs, holding registers, which are analogous both to analog outputs as well as kind of internal general purpose analog type registers. You'll see that it is one based in its addressing scheme. So coils start with address number 1 up to 10,000. Inputs starting at 10,001 up to 20,000, and so those addressing schemes, you've got capacity for about 10,000 each of the different types of address areas. That's with the traditional 5-digit addressing scheme. Now, somewhat recently, or probably 20 years ago by now, that 5-digit addressing scheme was enhanced with an available 6-digit addressing scheme, which provided up to effectively 65,000 different instances of each of the 4 different types of addresses. Again, Modbus only supports bit type or Boolean and word type or integer addresses. Okay, now let's take a look at the Modbus message frame. Okay, and that's what we've got represented there on the right in the blue table. So let's start with the slave ID. Now, the slave ID is a single byte, and that can have a legal value between 0 and 255. Now, in reality, the original Modbus spec called out only legal addresses of 1 to 247, where 0 is used for broadcasting and 248 through 255 are reserved. Now, over the past several years, those once reserved addresses have become more common. And while here at Horner, we still only support the original 247, at some point we'll probably have to add support for the others just because a variety of manufacturers have decided that they're going to use them. So to maintain maximum compatibility, we'll have to add support there. But traditionally, the slave ID with Modbus has been between 1 and 247, with 0 reserved for broadcasting, and most devices do not support broadcasting. Okay, moving on to the second data field there in the message frame. There you've got what's called a function code. Now, what is a function code? Well, again, it's a single byte, and it defines a few things. First, it defines the memory type to be accessed. Remember, there are 4 different memory types in Modbus: coils, inputs, both of those are Boolean type single bit entities. And then you have the word type entities of input registers and holding registers. So again, the function code will define which of those 4 memory types are going to be accessed, and it's going to also define the type of action that's going to be performed. Are you reading? Are you writing? Are you reading a single entity? Are you reading multiple? Are you writing single register? Are you writing multiple registers? Those sorts of things. So again, it defines the memory type and the action to be performed. The common function codes, the most common ones, are shown in that table there at the bottom on the right. In general, 90% of devices support at least those function codes, although there are some simple devices that don't support all of those. And there are also many other function codes that some devices support, some that are standard, some that are non-standard. So it's important to understand when you're interfacing or integrating a Modbus device into a system, which function codes does it support? And that's almost always something that you can fairly easily find in the documentation. Okay, so we've talked about slave ID and function code. Next, let's talk about the data area. And the data area is the one area that's going to vary in terms of size by n bytes. A maximum, where n is a maximum of 256. That means that for the serial version of Modbus Rtu, you can get up to 125 registers crammed into that data area. With Modbus TCP, because there are some added data fields there, or at least some added bytes that are needed, your maximum is 123 registers. But we'll talk a little bit more about the data field here in a few minutes. And then lastly, there at the end there, you see a 2-byte CRC, which is a cyclic redundancy check. What that is there so that the device sending the data and the device receiving the data can do a CRC calculation on what was sent or what was received to make sure that the number of bytes and everything seems to line up appropriately. That ensures effectively at least 99% accuracy of the data that was transmitted. So that's what you have there for your Modbus message frame. Now let's take a look about how that message frame is sent around. And let's start with the old-fashioned Modbus serial. Again, this is Modbus sent over a serial port, and it's sent really in a couple different encoding, with a couple different encoding methods, Modbus Ascii and Modbus Rtu. Now, regardless of which method you're using, you're going to have to set the baud rate to start with, because with a lot of modern protocols, there are things like automatic baud detection going on. Modbus is not one of those protocols. So in general, that is a manual process. You'll need to set your baud rate, data bits parity, etc., so that your master and your slaves are all using the same settings. Now let's compare and contrast Modbus Ascii versus Modbus Rtu. With Modbus Ascii, it uses ASCII characters to mark the beginning and the end of the transmission. With Modbus Rtu, it simply uses silence effectively. An amount of silence or a lack of transmission on the line that meets or exceeds 3.5 bytes of time. And depending on your baud rate, that time will vary. Okay, now Modbus Rtu today especially is much more common than Modbus Ascii for a variety of reasons. It's much more efficient, twice as much, for instance, and it's very popular with half duplex type communications, which is, again, one of the more popular ways of having a single master communicate with multiple slaves. Now let's just take a quick look at Modbus TCP versus Modbus Rtu. So with Modbus TCP, you no longer are using, silence at the beginning and the end of the message. There you've effectively added a header that marks the beginning of the Modbus TCP message that consists of about 6 different bytes. And we won't go into detail of what those particular bytes are. Just understand that that's kind of the main difference in terms of the message structure. Now, as you can see, it's pretty obvious that Modbus messages that are sent over Ethernet and Modbus messages that are sent over a serial line are pretty much, almost identical. So it's very easy to see why this protocol is so easy to understand. All right, now let's take a look at what a request and a response might look like. Now, Modbus is kind of a pull response type protocol. You're going to have a master, which is going to send out a request, and then you're going to have a slave, which is going to respond to that request. And there's a variety of different requests that could be made, and they're all going to use those function codes we talked about a couple slides ago for doing various functions, reading different types of data, writing different types of data, etc. Okay, so what we're looking at here is the portion of the Modbus frame that consists of effectively the function code and the data. We're not looking at the things before that or the things after that. That's really what we're looking at here, is the function code and the data. So let's start with the request sent out by the master. Okay, so in this case, the first thing that gets sent out is a byte that is the function code. And again, we're only talking about the function code and data portion of the message. So a function code is sent out along with the starting address for that function code. So in the case of function code 3, what we're talking about there is we're talking about read holding registers. Okay, so we need to know which holding registers we want to read. So that gets sent as the starting address as a 2-byte field. And then the next 2 bytes is the quantity of registers that are going to be read in this case. Okay, so that's what is sent out as a request. Now, as a response, if that is successfully received by the slave, it is going to respond with effectively a mirror or an echo of the function code, which is 3, and then the number of bytes that is going to be sending back, which effectively is the data or the values of those holding registers that were requested. Okay, and if there was a problem with the request, something that wasn't right, then instead of the response that I just described, you can send back instead, the slave will send back instead the error code. Now, keep in mind, in any one system, you can have a single master and multiple slaves. And again, we're talking about serial right now, so that means one master only. In the case of Ethernet, we can have multiple masters. But in this case, if you're talking serial, it's one master and multiple slaves. And regardless, if a slave receives a message that is not intended for it, it will ignore it. Okay, now let's take a look at a specific request, or a specific example of the request I just described of function code 3, where we're reading holding registers, and we'll fill in a little bit more of the data. Okay, so the request goes out. In this case, we're reading holding registers 40,108 to 40,110. Remember, holding registers are addressed from 40,001 on up. Okay, so we send a function code 3 along with the starting address, the high and the low byte, the number of registers we want to send in the high and the low bytes. Basically, it's a total of 3 registers that we're reading in this case. And then the response from the field, or from the slave, if you will, is again an echo of the function code followed by the number of bytes that is following. And then effectively, those 6 bytes represent the values of Modbus registers 40,108, 109, and 110. Now, there's some interesting things we can note from these responses that are that'll teach us important things about Modbus that'll come in handy later. One of those things is that Modbus is what's called a big endian protocol, or it uses big endian transmission. Now, what is big endian anyway? Well, there are 2 different types of ways in which data can be sent out over the wire. Most significant byte first, or most significant byte last. Big endian is most significant byte first. So you'll notice from those areas I've highlighted in red there that the order at which the bytes go out over the wire is high byte first, followed by low byte. And that's because Modbus is a big endian protocol. If it were a little endian protocol, then the low bytes would go out first. Now, another thing that you'll note that's very important is that what goes out over the wire is not address 40,108, but it's an offset from the beginning of the memory area. Now, we mentioned before that holding registers start at 40,001. So what is sent out over the wire is the starting register, not 40,001, but the offset from 40,001, which in this case, as you can see, is an offset of 6B in hex, all right, which is 107. All right, so that's what gets sent out over the wire. Now, why is that important? Most of the time when we're generating Modbus messages, we don't have to go to the trouble of populating all these data fields with bytes and things like that. When I show you the configuration later, it's going to be much simpler than that. But by understanding that offsets get sent out over the wire, you'll have a better understanding about why some manufacturers specify holding registers, for instance, with specific register addresses like 40,001, while other manufacturers will specify an offset of something like 006B. So while those look like completely different things, in reality, they're referring to the same thing. So that's why I wanted to point out to you that there's a difference between absolute register addresses and offsets, although they're pointing at the same data. All right, now let's talk about other data types. So far, we've talked about the fact that Modbus was designed with bits and words in mind. But certainly for a very, very long time, certainly, almost the full 40 years since Modbus was created, there's all kinds of other different data types other than those that can be easily represented by bits and words. So how are those handled in Modbus? Well, first of all, the spec does not necessarily define how those are handled. However, if you strictly consider that all data types just be constructed of 16-bit registers, then you'll kind of see how it really should work. So if you're dealing with bytes, well, that's half of a register. If you're dealing with Ascii, each Ascii character is a byte long, so you can therefore fit 2 Ascii characters per register. Integers, whether they're signed or unsigned, they still take up 16 bits or a word. It's just a matter of how they're interpreted. So Modbus, in reality, even though it defines everything as unsigned integers in the spec, it can be interpreted any way you want, in a signed or unsigned, if you're talking about a 16-bit integer. Now, for double integer entities that are 32 bits long but still are integer based, those are just 2 consecutive word type registers. Reals, which is the floating point representations of data that again is 32 bits long, is also 2 consecutive word registers, and long reals are 4 consecutive word registers. So again, Modbus does not specifically define how these other types are handled, but just consider that any type you come up with will effectively be made up of consecutive bit or word type data types. Now, again, why am I bringing this up? This seems like a lot of detail that maybe you don't need. Well, you do kind of need it, because the fact is that a lot of manufacturers want to support 32-bit and 64-bit, more commonly 32-bit, but sometimes even 64-bit data types, and they want to support Modbus. But the way that that data is sent out over the wire can vary by manufacturer. Okay, for instance, if you are a manufacturer and you've got 32-bit data that you want to be made available to a Modbus network, you effectively, when somebody sends a request to you for data, your number of registers that you are configured for a 32-bit entity should always really refer to the number of words. So it really should be 2 words equals 1 32-bit register. However, some manufacturers say, well, it's 1 register and it's 32 bits. So I'm going to say if somebody requests a value of 1 register, I'm going to spit back 32 bits. Again, a cause for confusion. Also, if you have a 32-bit value that needs to be sent out over the wire and properly interpreted by both ends, keep in mind that 32 bits is 4 different bytes, and there's potentially 4 different combinations in terms of the way or the order in which those bytes are sent out over the wire. Okay, so if you've got a value, for example, let's take a look at an example here. If you've got a value of ABCD hex, look in the upper right-hand corner. So let's say that you've got an OCS where register 1, %R1, is being handled as an unsigned double integer with a value of ABCD in hex, which is 43,981 in decimal. Okay, well, in the OCS, you probably know, if you've used our OCS before and you're using the old-fashioned register-based approach, that R1 as an unsigned double integer is actually going to be used by R1 and R2. So the AB part of the most significant portion of the data is going to be housed in register 2, and the least significant portion of the data is going to be housed in register 1. Now, assuming that we're going to respond to a properly formatted Modbus request from a master out there somewhere that wants to read register 1 as a unsigned double integer, well, for a properly formatted Modbus request, the number of registers requested should really be 2, and then we should send out R1 first and then R2. And the bytes should be ordered most significant byte first, least significant byte second for each of the 2 registers, because that's how Modbus is defined. So what we should send out over the wire in response to a Modbus request is the bytes should be in the order effectively of D, C, B, and A. And then on the other end, it should be interpreted properly by the master and reassembled as A, B, C, D. So that should be what happens. Now, because there are differences in the way some manufacturers interpret this byte order and this word order, not all manufacturers follow this. Now, does that mean that we're out of luck? Well, no, not really. In general, most Modbus manufacturers that are manufacturers of masters understand this scenario, and they provide flexibility in terms of how the data is reassembled in case some of the manufacturers are doing non-standard things. So Horner is no different. While as a slave, we respond in a predictable, consistent one way, as a master, we give you tools to reorder the words if necessary to make sure that everything gets reassembled properly if necessary. Now, 95% of the time, this is not going to be an issue, but for that 5% when it happens, you should know that you may have a checkbox to check to rearrange some words, to reassemble things the way the manufacturer of the slave intends. And that's primarily just for, again, 32-bit data. All right, now we've talked about Modbus in general. We've talked about the way that data is organized. We've talked about the way the frame is made up. We've talked about sending data over the wire, both from a serial standpoint as well as an Ethernet standpoint. Now let's talk a little bit, or quite a bit actually, about specifically how our products, the Horner OCS all-in-one controller, can be set up both as a Modbus server or slave, and then later we'll talk about it as a Modbus master. So let's dive in there. Okay, first of all, one question you may have is, all right, if I'm going to be accessing data from an OCS over Modbus, what Modbus registers or Modbus references should I use in order to access OCS data? Well, first of all, retrieving OCS registers over Modbus is easy because we make our underlying OCS registers pretty evident. A lot of our customers still use the kind of traditional memory-based register structure where every time they create a variable in their program, they map it to a specific memory location. Because of that, they're well aware of what memory locations they're being used for which variables, and there is a standard published OCS register map to Modbus register map, and you see that here on the screen. So on the left, you see all the different types of OCS memory types and the range in general in which they're supported over Modbus. The third column shows the Modbus reference address. Okay, the traditional ones, 10,001, 30,001, et cetera, and where each of the OCS reference types fit. The next column shows all the different function codes that are supported in the OCS. And then the last column talks about the offset. So again, if instead of accessing or wanting to specify in your master a specific Modbus reference like 10,001, but instead the master makes it easy for you to specify a function code and an offset, then the data in this chart in the last two columns will help you accomplish that. If what they help you configure is primarily Modbus references, you'll see those in column 3. Now, one note here at the bottom. One thing you'll notice is there's a variety of ways in which you can access general purpose %R registers. And those are all in the bottom of the chart there. And that's partially because of an evolution. When the OCS first supported Modbus, a long time ago, we only had 2,048 registers. So when we expanded beyond that, we couldn't just automatically put them in starting at 40,001 because we'd already used that register space for AQ registers, for instance. So again, you've got a few different choices when it comes to which memory addresses to use for %Rs, but they're all right. And if you have the ability to use the 6-digit Modbus reference instead of the 5-digit reference, that gives you access to the most %R registers, basically 10,000 of them, starting at 410,001. And again, just as I mentioned, you've got two different approaches for accessing these OCS registers, using the Modbus references or using the function code in combination with the offset. Use whatever one is convenient. They they all point at the same OCS register space. All right, now let's talk about configuration, and I'll show you how we do this configuration a little bit later, but frankly, configuration of an OCS as a Modbus TCP server could not be simpler. Of course, you have to configure your Ethernet. You're going to need IP address, net mask, etc., to be configured for the OCS in general. So, you're going to have that all set up. But that's true of any Ethernet protocol you use. But if you want the OCS to effectively reply to OCS queries that come in, then all you literally have to do is check the Modbus Slave checkbox under Resident Protocols, and you have a couple of additional options that are available under Configure Selected Protocol, where if you want to use UDP instead of TCP over Ethernet, that's available. And if for some strange reason you wanted to change the port number, you could do that as well. In general, you would almost never do that. And then another thing that you might want to do, however, you also have the ability to optionally assign a write protect bit, such that when that bit is on, it prevents any data from being written over Modbus. Now, of course, the other way of preventing any data from being written over Modbus is to just not support the protocol by not checking the Modbus slave block. But if you do want to support it, but you want to, either permanently or, on and off on the fly, enable or disable the ability of data to be written to the controller, you can utilize a bit to accomplish that. All right, now let's talk about using or configuring the Horner OCS as a Modbus serial slave. Okay, we're talking not about Ethernet. Now we're talking about the OCS responding to Modbus requests as a slave, but over, say, the RS-232 port or the RS-485 port. Now, to support that, it's still very simple, but it does require a couple of rungs of logic with using both a open function block as well as a Modbus slave function block. And these function blocks are accessible in Cscape from the communications section of function blocks in your toolbox for your instructions. So again, it's very simple. The open function block is used to select what port you're using, MJ1, MJ2, etc. Of course, you're going to configure baud rate, data bits, stop bits, etc. Are you using Modbus Rtu or Modbus Ascii? And again, by default, if you have an option, use Rtu. It's much more efficient. And then the Modbus slave function block is specifically geared towards assigning a Modbus ID. Remember, that's between 1 and 247, traditionally in Modbus. And then again, you also will also assign what's called a Modbus Timeout, which is the amount of time that a Modbus slave will wait in between messages from a master before it basically determines that the master has gone away and it takes corrective action, whatever that corrective action might be, in case the corrective action could be things like turning outputs off or those sorts of things. Okay, so setup's a little different for an OCS as a slave, but I'll show you these things live in Cscape a little later on. Now, let's take a look at mapping. How are the variables in your program mapped over to OCS and ultimately Modbus register space? Well, it depends a little bit on what style of logic you're using. If you're using the traditional register-based advanced ladder, well, every time you've created a variable, you've effectively had to map it to a memory location. And that memory location, if it's on the table that I showed just a minute ago, that the translation between OCS registers and Modbus registers, if it's on that table, then every OCS register has a corresponding Modbus register, so that's the one you would use to access that data. Okay, pretty straightforward. However, if you're using a more modern approach, such as our tag-based advanced ladder or our IEC logic, where you don't have to map or tag a specific memory location to every variable, then you've got a little bit of extra work to do. You've saved a ton of work by not having to map every register. Now you've got to do a little bit of extra work to take the variables that you do want to share over Modbus and map those to specific memory locations. And you do that from the program variables table, which I'm showing there on the screen, from the column marked tag, which at some point we're going to rename map. So what that shows there is that we've, in the top group of variables, none of those are mapped or tagged. So none of those are accessible over Modbus. Whereas the two on the bottom there, process pressure and process temperature, have been mapped over to internal OCS register space, which means they are accessible over Modbus. Okay, so again, you only need to map or tag those variables that you want to share on Modbus. You don't have to tag everything, obviously. Okay, now let's talk a little bit about 16-bit versus 32-bit. So if you'll notice there, that second variable on the bottom, process temperature, is a real variable. So we want to make sure the master on the other end hopefully will interpret that properly. So we've mapped it there to register 1001, but as those of you who use OCS regularly know, that real variable actually is stored in both 1001 and 1002. So the master will need to request 1001 with a length or number of registers of 2, and then effectively it'll receive both of those words, and then the master will just have to assemble those and then interpret them as a real value. So that's how that would be handled in this case for a master grabbing data that happens to be encoded as a real value. It's going to be in 2 consecutive 16-bit registers. Another thing to mention is as you individually map your variables to OCS register space so they're available over Modbus, you do not need to map them to consecutive locations. However, if you do map them to consecutive locations, you can make things much more efficient from your Modbus master to grab the data with much fewer messages than if you put everything all over the place in terms of the OCS register space. So keep that in mind. The more assembling in consecutive locations that you can do, the better off you're going to be. All right, now let's talk about using the OCS as a master. And this is probably, certainly from a serial port standpoint, this is probably the most common way the OCS is used. And it's also very commonly used on Modbus TCP as well. Okay, so when you're using the OCS as a Modbus master, you're effectively going to be configuring what we call a Modbus scanner. And again, I'm going to be going through live in Cscape these dialogues that I'm showing you, but I want to kind of introduce them to you first through this slide program. Okay, so you're going to be setting up a Modbus scanner. What is a Modbus scanner? Well, that is effectively functionality in the OCS where it is going to be automatically in the background retrieving, reading, and writing Modbus data while you are going about your business, or the OCS is going about its business, you know, and solving logic and showing data on the screen and all those sorts of things. Now, there's a couple different modes in which the OCS can perform this scanning or polling of Modbus data. Again, whether that's TCP or whether that's over serial, it's the same configuration method. It can be done automatically, where it's effectively just as fast as it can, it is going to be going out and scanning data from a series of Modbus slaves. Or it could be automatic, but being done on a periodic basis, like maybe every once per second, you're going to initiate a scan list and grab data, and then you're going to wait around until a second expires, and you're going to do the whole thing over again. Or another way you could be doing scanning is you could be setting it up to do it manually, so that it takes a trigger register or a trigger bit in your logic to instigate the scan from happening, or to instigate the scan happening. So again, you have a couple different ways you can configure your polling or scanning: automatic or manual, periodic, or as fast as possible. Another thing that's new with Service Pack 3, and we'll talk about Service Pack 3 at the end of the presentation, and that is you have the ability to enable or disable the protocol on the fly. So with Service Pack 3 now, you can say, all right, in this situation, I'm not even going to be talking Modbus. I'm going to go ahead and disable temporarily that protocol and then re-enable it later. Or you could use that as a way of fixing potentially a misbehaving system. How would you do that? Well, if you close effectively disable scanning for a while by disabling the protocol, you're effectively going to have the OCS close that port, that Ethernet port. And then when you re-enable it, it's going to open that port up again. With some misbehaving slaves, that could cause them to go back to behaving again. So that could be used kind of as a powerful way of effectively, you know, kind of restarting a slave that is not behaving properly. Okay, well, what else can I configure when I'm a Modbus master? Well, let's talk a little bit about that 32-bit data handling that I went through. And when we talked about the fact that, you know, we can send the data, the bytes, you know, in 4 different ways if we've got a 32-bit piece of data, you know, the ABCD thing. Well, we can adapt. When we're a master, we can allow you to adapt to different slaves that may handle that 32-bit byte order in different ways. So that's pretty powerful, okay? And if you have a slave where when you say you want to read one register, it's going to send back 32 bits, you can adapt to that as well. So again, we've added those capabilities in the master configuration to allow you to handle that. Also, another thing that we've done, which is really nifty, I've talked earlier about the fact that some slaves or that data sometimes is presented in absolute Modbus addresses, you know, 40,001, 30,001, etc., or sometimes it is expressed as an offset from a standard data type. Well, we allow you to configure for each slave that you're talking to, what style of addressing does it use? And I'll show you a slide here in a minute that'll show you how valuable that can be. And then, and of course, we're also, as part of your configuration, when you're using the OCS as a master, we provide you plenty of status information that you can read to keep track of, you know, what slaves are responding or not responding, what kind of error codes are you getting, those sorts of things. But getting back to the different styles of OCS, I'm sorry, of Modbus addressing, you could configure, or you might have, let's say, a slave, which is a variable frequency drive, which in the back of the manual for this variable frequency drive, there is a list of Modbus parameters that can be accessed. Drive manufacturer on the left uses 5-digit addressing. You see that there, 40,001, 40,002, etc. Drive manufacturer 2 uses decimal-based offsets in their manual. So we allow you to configure for each slave what style of addressing it uses. Even though it's pointing at the same data, you don't have to, in your head, convert from 5-digit addressing over to an offset or vice versa. You can just enter the data in that you want to read or write for that particular slave in its native documentation, if you will. Okay, so on the left, you'll see that when we enter in the data to be read or written, we're just going to type in, you know, 40,001, 30,001, etc. But the data field on the right, we're going to effectively access a decimal-based offset in conjunction with a function code, which is going to make it much easier for us to not accidentally make a mistake by misconverting between an offset and an address. The other thing that's kind of cool is if you happen to have 2 OCSs talking to each other over Modbus, which you can do, you don't even have to use Modbus addressing at all. You can configure that slave OCS or the master that's talking to the slave OCS to use native addressing, and therefore you're just going to type in the native OCS addressing styles of Rs, AIs, AQs, Is, Qs, etc. So that'll keep things simple as well. So again, we've tried to be flexible in the way that you configure the data that you want to read or write from the slave, and with a minimum of errors. Okay, a couple other things we want to cover. So we talked about the fact that you're going to set up a poll list, or I'm sorry, you're going to set up a Modbus scanner. You're also going to configure slaves to, you know, how to talk to the slaves, how their Modbus memory is listed in their user documentation. But then the last thing you're going to do is you're going to create what's called a scan list of variables. So you're going to make a list of, for each slave, what data you want to read or write. And you're going to create that what we call a scan list. And effectively, Each item in the scan list can consist of up to 32 consecutive Modbus addresses that you want to read or write. The fewer the scan list entries, the faster your response will be. So if you have a ability to read a chunk of registers with one read, for instance, you're better off doing that than having, let's say, 7 different reads for 7 different registers, if you could access them all with the same read. Again, the fewer the scan list entries, the better. Once again, there's some slight differences between using register-based advanced ladder or using tag-based or IEC approach. With register-based advanced ladder, you're just going to directly type in your local register. You're going to type in a local OCS register number, %R1, %R7, whatever, where that remote data is going to be read into or written from. If you're talking tag-based advanced ladder, the best way of handling that is to effectively set up 1 or more variable arrays in order to access that data in a consecutive fashion. And I'll illustrate that here shortly. And if you're grabbing data from a slave that happens to be 32 bits in nature, like a float or a double integer, there's a 32-bit access checkbox you're going to want to check that you'll see up here on the screen. Once again, I'm going to go through all of this live in Cscape here in a little bit. When you're creating your scan list, not only can you specify the data that you want to read or write and where you want to have that stored locally in terms of a variable or an array of variables, there's different functions that you can perform there. You can, the update or the scan list entry could be just a polled read, where you're reading data strictly from the slave. It can be a read/write, where you're normally reading data, but if the data changes locally in the OCS, you stop what you're doing and change it and perform a write function to the slave. There's a similar read/write called a read/write init. That's identical to a regular read/write, except that on power-up, the OCS will initialize the slave by writing the OCS's current value at power-up to the slave. So that way at power-up, if there's a difference between what the slave has for that particular parameter and what the OCS has for that particular parameter, with the case of a polled read/write init, the OCS is going to write its value to the slave at power-up so that they'll agree. Otherwise, with a regular polled read/write, the OCS is just going to start by reading whatever data that the slave is using and using that one instead at power-up. And then you've got a triggered read and a triggered write, which are just what they sound like, where you can assign a specific trigger bit to initiate a read or initiate a write. Okay, now there's one other way that you can use Modbus or any other, or a lot of other protocols for that matter, and that is to map it directly to graphics objects on a screen. So if you have, let's say that you're talking to a variable frequency drive. I use that example a lot because it's such a common example. There may be half a dozen different parameters that you're going to want to read and write all the time. What frequency is the motor running at? What is the target frequency I want it to be running at? Maybe you're starting and stopping it over Modbus as well. So those are things you're going to include in that poll list I just talked about, so that the OCS is continuously updating that data. But what about some of the set point or other type occasional Modbus data that you really aren't that interested in on a continuous basis? Maybe some PID parameters or a drive setting, something that gets set every blue moon, but that does not need to be continuously monitored. Well, for that scenario, one option you have is, instead of adding it to your scan list and making your scan list really long, you can strictly create objects on a screen that allow you to monitor or change that occasional data and directly access it over Modbus instead of even creating a local variable in the OCS. So in the square, the red square area in the upper right-hand corner there, you'll see that for this numeric data object, I'm directly accessing from VFD1, I'm directly accessing Modbus register 40,007. So I didn't have to put that into an internal register. I'm directly reading that over Modbus. Now, those Modbus registers will only be read or written while that particular screen is being displayed. They won't always be read or written. That way, I'm not, slowing down my overall communications by looking at data that I don't really need to look at very frequently. So that's another pretty nice way you can utilize Modbus with the OCS, really just like a traditional HMI, really. Okay, now let's talk a little bit, before we go into the demonstration, let's talk a little bit about how this, at runtime, how this kind of poll mechanism that we set up through our configuration, how that works. Okay, so let's say an OCS comes up from a startup, from stop to run. Okay, first of all, if the protocol is not disabled, remember that the ability to disable a protocol is a new feature we've just added in Service Pack 3, but if the protocol is not disabled, the OCS just starts executing the scan list. So, there's some early things it's going to have to do. It's going to have to establish connections with the slaves. It's going to have to open ports, those sort of background type things, but I'm not describing those exactly. I'm just describing really kind of the more obvious things in the foreground. So again, the protocol is not disabled. The OCS starts executing the scan list. It starts going through the scan list items one by one. Remember, the items on the scan list are things like, I want to read from slave number 1, registers 40,001 through 40,010, and I want to put those in these local variables. Then I want to move on and I want to read, these registers, et cetera, et cetera. So that's what I'm talking about when I'm talking about that scan list. So the scan list items are executed in sequence, one at a time. Once that scan list is complete, if there's any Modbus registers that are tied directly to screen objects that are currently being displayed anyway, those would be added and those would be scanned on the scan list as well. Okay, so I took the units that I've configured, or the data that I've configured to be scanned continuously, and then I've temporarily added to that any Modbus references that are currently on the screen. If there are no Modbus references currently on the screen, there's nothing that gets added. Okay, so once I get through my complete scan list and get through any screen registers, I'm gonna go back to the front and do it all over again. Now, if I've set up the Modbus scanner to scan as fast as possible, it's gonna do this on a continuous basis. If I've set it up to scan on a periodic basis, let's say every 5 seconds, once I finish my poll, I'm gonna wait for 5 seconds to expire before I start the next scan or start the next poll. So that's the difference there between going as fast as possible and going on a periodic basis. But most people set up Modbus to go as fast as possible. Okay, now another thing that can happen, or there's a couple things that can happen while we're going through our scan list. If at any point, data that is configured for read/write, if at any point, if any of that data changes in the OCS, in other words, it's been changed in the OCS, maybe from the screen or from the ladder, the OCS will interrupt the scan list and immediately write that new data value to the slave, okay? And then, of course, verify that that write was successful. So that's one of the things that can interrupt the scan list of polling a bunch of registers from a series of Modbus slaves. Another thing that can kind of interrupt things is if at any point you have message failure. So you attempt to execute part of your scan list, but for whatever reason that fails. Maybe there was corruption on the line, maybe the slave was powered off, whatever the case may be. Okay, so in that scenario, the OCS is going to retry the message as we've configured it. And I'll show you in a second how you can configure retries. If you haven't configured any retries, it won't retry. But anyway, it'll continue retrying until either that message is successful or until it's run out of retries. At that point, it will take that problematic slave offline and it will ignore that slave until it's time to reacquire the slave. And a reacquire time is something else that we can configure. Okay, enough of this talking and walking you through these sort of things with slides. Let me show you how we do this in Cscape. Okay, so hold on one second here. All right, let me go ahead. First thing I have to do is find my mouse. There we go. All right, let's start off with, I've got a OCS and I want it to be able to act as a Modbus slave over a serial port. Now, this is not something you're going to do very frequently. It's probably one of the more rare ways that an OCS is used these days. Most of the time, if an OCS is a Modbus slave, it's a Modbus slave over Ethernet, not over a serial port. But I want to show you that functionality anyway. So again, like I showed on the slide, to enable Modbus Slave over a serial port, you need to have two rungs that you create. One that utilizes the port open function block and one that utilizes the Modbus Slave function block. And these both can be found from the COM operations section of the toolbox with all the instructions here. Here's the open COM port function, and here's the Modbus Slave function. Now, keep in mind, there also is a Modbus master function block that is workable. It does still work, but these days it isn't used that frequently. It's most commonly used. It was the original way that we did Modbus master protocol, but today it is only really used in those cases where an application engineer wants to strictly control every aspect of polling a slave or a series of slaves, so he may want to roll his own Modbus scanner. But that's a pretty rare scenario. A much more common scenario today is they're going to set up the Modbus scanner like I'm going to show you here in a few minutes. But I wanted to at least point out that that function block is still there and it's still functional. Okay, the OCS open function block, all right, this is the configuration parameters for that. Okay, and it's really mainly just what port am I using. Keep in mind, most OCSs have at least 2 serial ports, some of them 3 or 4. So which serial port am I using, and then what's my communication parameters? And once again, you're going to use Modbus Rtu every chance you can, and half duplex multi-drop every chance you can as well. Okay, so you'll set up those parameters. You'll have a coil that turns on when the port is successfully opened. That contact off that coil will also enable Modbus Slave. And the only things to configure there in this function block, let me double click on that, are the Modbus ID, which is going to be somewhere between 1 and 247, a timeout value in milliseconds, which is how long the slave is willing to wait for a master to poll it on a periodic basis. And if that master quits polling on that periodic basis, we'll get a flag on our status register that basically says, hey, the master went away, and then we can decide to take corrective action if necessary. And then we'll also assign a series of, or a single status register for monitoring that communications. So that's all that's required for setting up a OCS to be a slave on serial Modbus. Okay, wanted to show you that. All right, next thing all the rest of our communications and talking is gonna be about, really all about using the OCS as a Modbus master. And specifically, we're gonna talk about Modbus TCP master, all right? But the same configuration method for all intents and purposes applies to both. All right, so let's start out by showing, all right, where do we configure an OCS to be, well, let's start with the Modbus TCP slave. Let's do that first, because we did the Modbus serial slave. Let's spend the 5 seconds to show you how to be a Modbus TCP slave. And keep in mind, you can be a slave and a master at the same time, which is pretty common, actually. You could be a master over a series of variable frequency drives, and you could be a slave to a SCADA package, for instance. Okay, so we go to LAN 1 in the case of, I've got an EXLW here that I'm configuring. So we go to LAN 1, hit config. All right, in this case, again, I'm using Service Pack 3, which we'll talk about in a little bit. So I'm just going to go ahead and use DHCP to set up my Ethernet. You know, I could have manually configured all these things or used variables or whatever the case may be, but today we're talking about Modbus TCP, not necessarily about setting up the rest of the Ethernet stuff. Okay, so if I want to be a Modbus TCP slave, all I literally have to do is check this checkbox under resident protocols, Modbus slave. And this is Modbus TCP slave, remember, okay? All right, and there's a couple options I can configure. Most commonly, I don't need to configure them, but I highlight that here and hit configure selected protocol. I can switch to Modbus UDP if I want. UDP is effectively, it does not use TCP, error checking and all those sorts of things. It's sometimes more popular over cellular because you can control how many bytes you send out over your cellular account better than you can with TCP. But again, it's not as commonly used as Modbus TCP, but it is available. Again, here's the port that you're never going to change, more than likely. And then here is the ability to add a write inhibit bit, where when it's on, we will not accept, as an OCS Modbus slave, we will not accept writing of data into our memory table. So if that is set, we will not accept writes. If that bit is not configured, or if that bit is not set, then we will respond appropriately to write requests that come in over Modbus TCP. Okay, so that's all that's required for configuring a Modbus slave. Now, as I mentioned a second ago, we can be a Modbus slave and a Modbus master with the same OCS. So let's show you how to do that here. All right, we've already configured Modbus slave. Now let's go down here under downloadable protocols, not resident protocols, but downloadable protocols. And what's available on the list here is Modbus TCP client. Remember, client is analogous for master. Okay. All right. And we've got 3 levels of configuration that we're going to be able to do as the OCS as a Modbus TCP master. Let's start on the network level. Okay. All right. First of all, up here in the upper left-hand corner, this is your port ID, maximum port, minimum port ID, maximum port ID, keep alive time. In general, you don't need to mess with these things. The defaults should be perfectly fine. Okay. Here is where you can select between Modbus TCP or Modbus UDP. So when we're a master, we can be a UDP or a TCP master. Okay. This is where we're going to configure our timeouts and our retries. Okay. All right. So if we send a message to a slave, remember we're the master here, we're going to wait a certain amount of time for that slave to respond. Now, if the slave is powered off, it's never going to respond. Okay. So we want to be careful and not set this timeout to something that's too high. Now, this is set right now. It's in milliseconds. This is set to 10 seconds. That's the default. Frankly, that's too high. If I was setting this up, I certainly would probably set something up closer to a second. Now, when would I maybe set a longer timeout than that? Well, if for some reason I'm doing Modbus TCP over a complicated network that may even be going out over the internet, I could have some delays from time to time. Or if I'm over a cellular modem, I could have delays from time to time. A lot of cellular modems these days are just, Ethernet-based cellular. Then in that scenario, I might want to bump it up above a second. But all other cases, I think I would keep it at 1 second or maybe even a little bit shorter for a timeout. Okay, maybe 2 seconds max. So let's set the timeout here at 1 second. So what that means is when we send a message to a slave, if it doesn't respond within a second, then we assume that it's not going to respond for that particular message, and we will retry. Now, this is how many times we will retry, anywhere between 0 and 255. I think the default of 1 here is probably pretty good. Okay, that means if for whatever reason a message gets lost or damaged, we'll retry at least once without holding things up too long on the network and before we take the node offline and move on. So I like a value of 1 retry here. Okay, so this is how many times under the normal polling of a slave, how long we'll wait for it to respond and how many times we'll retry. Now, let's say that it doesn't respond and we do a retry and it doesn't respond again. Okay, at that point, we do what we call taking the node offline, and we'll ignore that node until what's called a reacquire time has basically expired. Now, this is set up again in milliseconds. The default is 100 seconds. So that is basically saying that it's going to ignore that slave and move on our merry way, talking to other slaves. And then 100 seconds later, it's going to try again to talk to that slave, and it would effectively try twice because, again, we've configured 1 retry. And then again, if it doesn't reply, and the retry fails again, then we'll take it offline again. So that's what the reacquire time is. And if you only have 1 slave, there's no reason having a fast or having a long reacquire time. You might as well just keep pounding away trying to talk to it. Okay, especially if you're talking a private network that's only between these 2 devices. If you've got multiple slaves, then a reacquire time is probably a good idea. Okay, that's a little longer than the minimum. All right, so that's what our timeouts and retries, or where our timeouts and retries are configured. All right, now let's take a look at what we call our scan configuration. Remember, what we're calling a scan is a process in which the OCS is going to be effectively, on a periodic basis, reading and writing data to one or more slaves. Okay, so if we set it up for the default of automatic with an update interval of 0, that basically means we're going to be updating through that scan list as fast as possible. And most of you will probably use that setting. Now, if you don't want it to be as fast as possible, you'll change your interval from 0 to some number of milliseconds, maybe 1,000 or 5,000 if you want to retry every second, or not retry, if you want to periodically scan every second, every 5 seconds, whatever the case may be, okay? Or you could configure up a manual scan so that the OCS isn't just automatically going in the background, scanning the slaves, but that you've got to trigger it somehow from a variable. So if you're going to want to set it up that way, you're going to select manual, and you're going to set up these variables for trigger and ID select. Okay, but again, most of you are probably going to go ahead and let the automatic scanner do its job. And then this disable network is, again, new for Service Pack 3. Its function is to take Modbus TCP down as a whole, which has the same effect as closing the Modbus TCP port and then reopening it again once it's re-enabled. So you may want to use it for that. And then you've got the ability to support up to 4 status registers or status variables, which are going to give you feedback for things like, you know, what is the turnaround time on my Modbus scan list? 50 milliseconds, 100 milliseconds, 150 milliseconds, whatever the case may be. How many good messages do I have going, have I received? How many corrupt messages have I received? How many times have I received no messages at all when I send out a query? Those sort of statistics are what you're going to get with your Modbus master status. Okay, so that's configuration on the network level for Modbus TCP. And again, the register for, or the variable for disabling the network, which is 1 bit, the variable for status, which is 4 32-bit variables, those are optional. They don't have to be configured. I highly encourage you to configure them though. Okay, so that's the network level of configuration. Now let's take a look at the device level of configuration. Now this is where we add information about all the different slaves that we're going to be talking to. It might be 1 slave, it might be a dozen slaves. It all depends on your application. So let's take a look at what are the various things we can configure for each slave. Okay, so this is a slave I've already configured. All right, first of all, I can give it a name, just a convenient name, so I know what that is. That name doesn't go out anywhere, but it's used when I'm when I'm looking at this configuration. So in this case, it's set for slave 1. Again, we're talking Modbus TCP here. I've got a target IP address. Now I can hard code the IP address like I've done here, or I can actually enter in a variable here so that can be configured from a screen, for instance. Okay, so that's probably the better way of doing it. In this case, though, I've just hard coded it. The target port, which is almost always going to be 502, because that's the standard Modbus TCP port, is configured here. If I want that to be a variable, again, I can assign a variable to that. And then we have some Modbus TCP slaves also require a unit ID that is more than just the IP address. That's also more or less a slave ID. So if you have that scenario, you can check this checkbox and configure that slave ID somewhere between 1 and 247. Okay, this is where we configure the details for your specific slave that either may misbehave a bit when it comes to handling 32-bit data, either from the standpoint of swapping words in an unexpected fashion. Remember, there's all those different ways from a word and byte order that the data can be configured. Or when you ask for reading a Modbus register with a length of 1, it might send back 32 bits of data instead of 16 bits of data like it should. So you have that checkbox you can check as well. And then here's where we can configure what's the style of addressing that it uses. And that's from that one slide where, you know, if you've got a Modbus, a traditional Modbus device that uses 5-digit addressing, like most devices do, but not all. You would select this checkbox. If it's using generic decimal addressing with an offset, you would select that. If you're talking to another OCS and you don't even want to use Modbus registers at all, you can natively type in the OCS register types of R's and M's and T's and all those sorts of things. Okay, so that's what those are for and where those are accessed. And then again, you've got a disable bit for that slave, which is new with Service Pack 3, and you've got a status register, which is 2 consecutive word type registers, which effectively tells you a little bit about how well it's working on a continuous basis. And then down here, if you want to stop talking to a slave when you get an error, you can select this checkbox, or you can go ahead and retry as you've configured. All right, so that's configuration of an individual slave. All right, now again, we could have multiple slaves here, but in this case, I'm just showing one. All right, now the third level of configuration, again, we've configured the network level and the device level. The third level of configuration is the scan list. All right, and here is where we specify what data we want to read or write, and we can set up a whole series of transactions that we want to occur. So here, let's go ahead and assume that we've got slave number 1. That's the only slave I've configured. And I want to configure or access its Modbus registers. Now, how do I enter that here? Well, if I'm trying to remember how to enter it, I can press this little help button here, and it tells us, oh, okay, that's the format I need to enter that in as. So I could easily add this in by looking at the user's manual for my device, and the data I want might be starting at 40,007, and I might want to read 6 consecutive registers here. Now, where do I want to put that in my local memory? Now I'm showing you how to utilize Modbus TCP with our tag-based ladder editor. So I'm using tag-based variables. So I'm going to go to the variable selector here. Okay, and I've previously created something called slave 1 holding registers. That's a variable, that's an arrayed variable. So there's, in this case, up to 32 different word type registers, all consecutive from 0 to 31. I'm going to go ahead and select the first one here, which is sub-0. Okay, and so what that means is Modbus registers 40,007 through 40,012 are going to be located or copied into slave holding registers sub-0 through sub-5. Okay, 0, 1, 2, 3, 4, and 5. Okay, so I'm reading in six consecutive words. Here's where they're coming from. Here's where they're stored locally. If this is strictly a read, I'm going to leave that as a polled read. If I want to read it normally but be able to write it when it changes, I can select a polled read write. If I want the value that's in the OCS to be the one that's used at power up, if there's a difference, I would select polled read write init. And if I want a triggered read or a triggered write, I'd select one of these over here. Okay, so that's configuring an item in the scan list. And here you can see I now have the local data, where it's coming from, how many words it is, and in this case, this little icon indicates it's a read write. All right, so we're done there. I could add, and normally I would have a whole series of different additions to the scan list, but I'm just going to leave it at 1 for now, just as illustrative. Okay, last thing I'm going to show you live is how to directly add Modbus data from the screen. So I'm going to go ahead and pull up the screen here. And I don't have anything configured in terms of screen objects or anything like that. But let's go ahead and add a data object. And let's say that we want to be able to set the value that's in Modbus register 40,001 with this data object. And maybe that correlates to motor speed. Okay, so instead of selecting internal register for my data source, I'm going to select slave 1, ETN1. So that tells me the name of the slave that I named when I configured the slave, and ETN1 is telling me that's coming from Ethernet port number 1 or LAN 1. Okay, now I'm going to type in my Modbus variable directly from this guy. And if I don't remember how to type those in, I can again press this little help button here, and it reminds me, that's right, I can just type it in directly. So it could be 40,001. All right, and I'm just going to read in one 16-bit value. I'll use a slightly larger font here. It's going to be, let's say, read write is okay, and I'll give it a legend of motor speed. And without spending a whole lot more time here, I'll just keep it simple, and there we go. Okay, so now I've created a data field which directly accesses not an internal OCS variable, but directly accesses a Modbus variable from a Modbus slave, and it only accesses this data while this particular screen is being displayed at runtime. So if it's not being displayed at runtime, that data is not being normally read or written. Okay, so that is what turned out to be a fairly lengthy demonstration and explanation of Modbus protocol. Before we get into questions, I have a couple things I want to go over here quickly. From a frequently asked questions standpoint, can an OCS be a Modbus TCP server and a Modbus TCP client at the same time? Absolutely. Can multiple Modbus TCP masters access an OCS that's acting as a slave? So not just one, but multiple masters. Absolutely. Can the OCS support multiple Ethernet protocols at the same time? Say Modbus TCP, Modbus or Ethernet IP, maybe FTP or email? Absolutely. We can support up to 16 simultaneous connections. Now, a couple things we can't do that I want to point out. We don't yet support a Modbus TCP write-only function that is not triggered. That's something that's been requested. It's a good idea, but we haven't done that yet. And then we also currently don't support any Modbus slave, TCP or otherwise, that requires a non-standard Modbus ID between 248 and 255. So that's something we don't support yet either. Believe it or not, Schneider, who I guess in theory acquired Modicon years ago, and of course Modicon's the one that invented Modbus, Schneider is now using IDs above the normally legal limit of 247. So I guess we'll go ahead and have to add support for those pretty soon. All right, before we get to the questions and answers, a quick announcement, because I know you're going to ask for those of you who hung with me here. And that is, where the heck is Cscape 9.9 Service Pack 3? That should have been out by now. I agree, should have been out by now, but we're almost there. I know, promises, promises. For those of you who aren't familiar with all the things that are included with 9.9 Service Pack 3, we're rolling out kind of the early version of Cscape registration, a lot of improvements to tag-based programming, the ability to enable and disable your protocols like I've shown here with Modbus TCP, improving the number of objects per screen with the micro OCS, adding web encryption to the micro OCS, adding support for DHCP and DNS, adding MQTT Sparkplug support, which has been asked for a lot. Those are all the things that are going into Service Pack 3. And I would say I promise, but I've been around too long, but I've been assured it is to be posted on the web Monday. And along with firmware 15.4 for all the Linux-based XL series products, which is XL4 on up, including the X5, the micro OCS series products, and the XL Plus. So those will be on Monday, and I will make sure that early next week at the very least, we send out an announcement email, or I'll work with our marketing team. I'm sure they've already got it planned to make sure you know that those, that not only is 9.9 Service Pack 3 on the web, but also that the appropriate firmware that enables all those new features is there as well. Okay. Now, finally, sorry this took longer than I expected, but let's get to the question and answer section here. Okay. Meanwhile, one thing I will mention is that Marcy, I believe, is going to launch a poll that will ask you a question about what networks you've used recently. So she'll be launching that here pretty soon while I answer questions, and you'll see it here on the screen. Okay, let me take a look at some questions. Are we going to upload the webinars on YouTube so we can watch them later? Absolutely. Marcy will be able to do that, and will do that soon. Let's see. Can we share the presentation? We will also share the presentation as well. For those of you who are channel partners, we post it in our normal channel portal area. And for those of you who are not channel partners, if you make a request to your local sales guy, we will accommodate you. Let's see. When the OC, here's a very good question. Peter gets an A+ for a good question here. When the OCS is a slave over Modbus TCP, how do we read registers 10,000 to 49,999? Well, the answer is you can't. We have to enhance our driver to support registers above 10,000. It doesn't currently support those. So that is the current answer. And if it somehow has been added, support has been added, nobody has told me. So I'm pretty sure it's still not supported yet. But that's one of the enhancements that we want to add, along with some of the other things I mentioned in my frequently asked questions area there. Let's see, when using tag-based logic, do you have to map each register individually? What if you need to read hundreds or thousands of registers? No, you do not have to map them individually. You can use register arrays to do that. So effectively, what I showed in Cscape was I showed reading 6 consecutive registers, Modbus registers, into an array, starting, in my case, I started at 0. And it read all 6 of those registers in with a single read into basically an array of registers, or an array of variables, I should say, or a variable-based array. So yes, you do not have to individually map those. Where you might decide to do some mapping is if you have to do some interpreting of data from integer to, say, double integer or float. Then it's easier to check that 32-bit checkbox and read them in individually, but because that isn't very efficient, in that scenario, what you probably would want to do is still read it into an array of variables, just like I showed, but in the variable window or variable editor within the tag-based version of Cscape, you would use the mapping column or the tag column to go ahead and map the variable that you want to convert over from an integer to a float or something. Let's see here. Okay, we had a user that was having trouble at one point getting Modbus TCP to scan automatically. So generally that shouldn't be a problem. I've used it many times and have been able to get it to scan automatically. If you're having trouble getting it to scan automatically, it could indicate a number of things, including a bug, I suppose, that you may have uncovered accidentally in your specific configuration. But in general, if you can't get it to scan automatically and you've configured it to do that, then get a hold of one of our application engineers and we'll help figure out what happened there, because it absolutely should work that. Okay, here's a question about assigning, when you're using tag-based logic and you want to read in the status, how do you do that when the status is 4 consecutive 32-bit registers? Well, that's another case where you set up a variable, say called master status, that is an arrayed variable. So you set it up as 32-bit data type, unsigned double integer, because that's the type of the status register, and then you give it a dimension of 4. So now you have status sub 0, sub 1, sub 2, and sub 3, which is where the 4 different status or parts of the status information will be shown. Okay, what else do we have here? Let's see. When the OCS is configured as a slave, will it support having multiple masters pull it at the same time? Absolutely. Why the different terminology between client master and server slave? Okay, it's just kind of a leftover between, I mean, a lot of people are, especially old timers, and I have to consider myself an old timer. A lot of old timers, we get thinking in terms of masters and slaves. And we have to pause for half a second when we talk clients and servers. So when I do a presentation like this, I like to list both of those, even though technically for Modbus TCP, client and server is the really correct nomenclature. If I list both nomenclatures, then sometimes people catch on a little quicker, including myself. Okay. Let's see, can you use a screen variable for serial Modbus? Absolutely. So it doesn't have to be strictly for Modbus TCP. Okay, so here's a question about our Modbus IO. Oh, about SmartRail. Okay, all right. So this customer mentions the fact that, and he points out rather accurately, that we do offer SmartRail Remote IO with an Ethernet option, and in reality, that Ethernet option is Modbus TCP based. Now, in general, Modbus TCP isn't the ideal IO network. You know, as I mentioned, it is, 40 years old. And so it's not the ideal IO network. Now, can it be effective? Absolutely. Absolutely it can. But there are some other more modern protocols that probably do better with IO, for instance. Now, we do utilize Modbus TCP for our SmartRail Ethernet version, but we also have other options, such as Cscan, our CAN-based protocol, that really, if all you're looking to do is just add IO that is easy to add and super efficient and fast responding, then that's probably as good an option as any. So for me personally, I generally, as a first choice, will recommend Cscan IO by default, unless there's a compelling reason to use Modbus TCP-based IO. However, there are compelling reasons in some cases. For instance, it could be that you've got an application where it's going to be way easier to wire up the Ethernet for the remote IO than CAN, okay? Such as maybe a lighting application where your remote IO is distributed quite heavily. So that might be a very compelling reason for using Modbus TCP instead of Cscan, for instance. So again, there's different strokes for different folks, different application cases for different networks, okay? If I'm getting ready to deploy an OCS system, should I upgrade to 9.9 Service Pack 3 before deployment? Absolutely not. And I'm not saying not as in don't do it. I'm saying you shouldn't wait unless there's a compelling reason why there's something you want to wait for. Okay. My general attitude towards firmware updates and Cscape updates is not always use the latest of everything no matter what. Now, that's not because I don't have confidence in our software or our firmware. It's because I'm a control engineer by experience and by heart, and I understand that you should really take a system that's working well and only upgrade it if there's a compelling reason to do so. There's a new feature that I really want to use. There's a bug that they fixed with the latest version that I really want to fix. Those are the reasons why I do updates on deployed equipment or equipment I'm getting ready to deploy, which is different than downloading the latest version and working on it on my PC when I'm not imminently getting ready to ship a system tomorrow without adequate test time. So I hope I answered your question. I have tons of confidence in 9.9 Service Pack 3 and in 15.4 firmware, but if I'm deploying a system tomorrow and have limited test time, there's no way I'm deploying it with those software and that firmware tomorrow unless I test it. And I say me, I mean me as a control engineer with a machine I'm getting ready to deploy. That's just good common sense. Okay. Good point from Edson that, yay, we're getting it on Monday. Christmas seems like it would have been sooner. I would agree. Another point made by Ed was that BACnet MSTP and BACnet TCP IP are interesting protocols. Absolutely, and I'm sure we'll do a webinar on that at some point. Another question from Ed, just to clarify, for scan list efficiency, should we scan one set of variables with a length of 5 instead of 5 individual entries in our scan list with a length of 1? If we can do that, absolutely do it. It's much more efficient that way. Okay. Is there any specific criteria for the dial-up modem spec when a Modbus Rtu master, or when a Modbus master wants to talk to a Modbus client via RTU protocol? Oh, there's the Wayback Machine for you. I mean, I've done a ton of Modbus over modems over the years, but nothing recently. Let's see. Anything specific for the dial-up modem spec? I would say just get something you can test before you have to deploy it. I'm not even sure who manufactures telephone modems anymore these days. I know they're being manufactured, don't get me wrong, but I'm not sure who's doing it. So just get one that you can test, that the manufacturer will let you test, and if it doesn't work, let you send it back. That'd be my advice. Sorry, I wasn't very specific on that. When would you use TCP versus UDP? UDP has less overhead, but UDP does not have any guarantee of delivery. So you would use TCP instead of UDP if your slave or your master didn't support it. A lot of Modbus devices support Modbus TCP. Only some Modbus devices support UDP. So that's, or maybe it's a scenario where I want guaranteed delivery. I'm not polling very frequently, so I want guaranteed delivery, and TCP gives me that. Let's see. Follow up to that modem question. When a Modbus master wants to talk to a Modbus slave over Modbus Rtu protocol. Let's see. Specific settings for the telephone modem. I'm going to have to defer that one for later. I think the last time I used Modbus over a modem, I used Modbus Ascii. So I'd want to defer that answer. I'll try and get you an answer through email. Will OCS work with all Ethernet IP devices? We support Ethernet IP in a variety of ways. That's not the subject of this webinar, but we support it as an Ethernet IP I/O device. We can exchange Logix tag data with a Logix CPU from somebody like Rockwell, but we are not an Ethernet IP scanner directly. So if you need an Ethernet IP scanner, you'll have to use a third-party product connected to the OCS Ethernet port over like Modbus TCP from somebody like Real Time Automation or HMS or Hilscher to handle the Ethernet IP scanner duties, while the OCS controls the scanner. So that's hopefully that answers your question. But if you just want it to be an Ethernet IP I/O device, we can support that all day long, no problem. If you just want to exchange Logix tag data with a Rockwell processor, we can support that all day long, no problem also. Regarding multiple messages at a time, you might want to mention it will only write out one change at a time. Absolutely, good point there. It only does one write at a time. Okay, it doesn't do multiple writes simultaneously. Another enhancement I'm sure we'd like to make to our Modbus driver is to support some of the newer function codes which allow you to do some simultaneous reads and simultaneous writes. Okay, that's it. Thank you for your feedback on the poll questions. You can see that Modbus TCP and Ethernet IP at least are still the most popular networks, although there's certainly plenty of Profinet, EtherCAT, and other networks out there. I apologize for the length of the webinar. This one a little longer than I had thought, but thank you for joining us.